Hey, what's up, class? So I said I'd make a separate little video about pH and what's happening there because it's one of those things that we, once again, kind of take for granted, but we don't understand what it actually is. Okay, so let's talk about what pH is. So, water can also disassociate from itself. So pH is actually just a measurement of the relative concentrations of two different molecules. All right, the first one is going to be H+, so that would be a proton. So when a hydrogen loses its electron, all that's left is just a positively charged proton, and we represent that like this, H+. Okay, so then if one of these H's from our H2O splits off and is doing its own thing, it's hanging out, it's a positively charged proton, that's going to leave behind this thing known as a hydroxide ion, which is going to be negatively charged. The reason this is negatively charged is because our oxygen here has stolen this guy's electron, all right? So if you add an electron, it's going to give you a negative charge because an electron has a negative charge. So once again, just to recap, H2O can disassociate from itself, and what gets left behind is a positively charged hydrogen ion and a negatively charged hydroxide ion. So this is happening all the time in water. Okay, the reason for this is oxygen is greedy. It really wants those electrons, and sometimes it wants those electrons so badly that it ends up breaking its polar covalent bond, and it just ends up covalently bonded to one single hydrogen, and the other hydrogen is like, I'm out of here, take my electron, whatever, I'm going to go do my own thing. So normally in water, the concentration between our protons and our hydroxides are pretty much going to be equal, and we call that neutral, okay? Now, if our concentration of hydroxide ions or our concentration of hydrogen ions is higher than our hydroxide, then water is going to be acidic. So if there's a lot of protons, water is acidic. The flip side of that is if our protons are going to be lower than our hydroxide ions, then water is going to be basic. So what does that really mean for us? Well, it gives us this scale here, okay? So we use the pH scale to determine how acidic or basic a solution is. So it's telling us the relative concentration of hydrogen versus our hydroxide. Okay, so 1, extremely acidic, 7, that is neutral, 14 is going to be basic. So take a look at our pH scale here. Now, the thing you want to be aware of is that every single change on the pH scale is a tenfold change. All right? The reason we represent it from 0 to 14 is because that's about the number of hydrogen ions and OH ions that we'll see in water. All right? So the relative concentration, basically here you're looking at a whole bunch of protons. Basically here you're looking at a whole bunch of hydroxide. This is a logarithmic scale, so each change here is going to be a tenfold change. So a lot of times students get confused because they think a higher number actually means that it's acidic, and they think that a lower number means that it is basic. You have to remember this is about decimals, so we're talking about things getting smaller and smaller and smaller. So we define pH by the number of hydrogen ions. So 10 to the negative 1, remember that's making a decimal, 10 to the negative 1, that's a relatively high concentration of ions, whereas if we go all the way down here, 10 to the negative 14, that means there's not going to be that many hydrogen ions, okay? It's going to be very, very basic. So let's take a look at this really quick. So a pH of 1 to a pH of 2, what's the difference there? It is going to be a 10 times difference. So there's going to be 10 times less hydrogen ions at a pH of 2 versus a pH of 1, a pH of 8 versus a pH of 7. There's going to be 10 times more hydrogen ions in a pH of 7 versus a pH of 8. And if we look at this one, a pH of 10 to a pH of 8, there's going to be 100 times more hydrogen. If we have a pH of 8, okay, there's going to be 10 times more hydrogen ions than a pH of 9. If we have a pH of 10, there's going to be 10 times less hydrogen ions than 9. So the reason we know it's 100 more times, there's 100 more times hydrogen ions in 8 versus 10, because if there's a 10-fold increase here and a 10-fold increase here, you're actually doing 10 times 10, so there's 100 times difference. So if you jump from 8 to 9 to 10 to 11, now you're doing 10 times 10, which is 100 times 10 again. It's a 1,000-fold increase. So this is a logarithmic scale. That means everything is increasing by 10-fold. So remember, we're talking about molecules and a concentration of water here. So there's a lot of molecules that we're talking about. So that's why it's a logarithmic scale. All right. So buffers and cellular regulation. So the pH of cells must be kept around 7. Why? It's pretty simple. Let me go back here. It's pretty simple why things need to be kept around 7, because you don't want a whole bunch of ions floating around in water, because then you're going to have a lot more chemical reactions happening with those ions. So if there's a bunch of positively charged hydrogen floating around, now anything that has a negative charge is going to be more easily disassociated in that solution, right? That's why acids are so dangerous. Okay. At the same time, something that's really basic is also going to be dangerous, because if there's a bunch of hydroxide ions around, a bunch of negatively charged hydroxide ions around, like in bleach, right? Bleach can also burn you the same way hydrochloric acid can burn you, because bleach is going to be pulling positive ions away from your skin, and that's going to burn you. And the flip side is hydrochloric acid is going to be pulling negatively charged ions off of your skin, which is also going to burn you. So either way, it's very bad. We need a balance here, and that gives us something right here, like what's happening in us. Pure water, 7. Blood, 7. So we want an even concentration of that H plus and OH, so that way chemical reactions don't kind of go out of control and form all these ionic bonds. So that pH can affect the shape of molecules. And if the shape, this is an extremely important thing to remember in biology, is that function follows structure. So if the shape of a molecule changes, so if the structure changes, that's going to mess up the function of it. Okay? So imagine you have a protein. Let's say my hand right here is a protein, and its job is to grab a fist like this. Well, if you change the pH, and parts of this start getting peeled off to go hang out with maybe some hydrogen ions, now this fist is going to punch right through my hand, and that's going to be a problem. Okay, that protein is no longer going to work. So pH has a huge effect on cellular function. The body, all life, is going to control the pH by basically keeping a reservoir of a bunch of protons hanging out in order to change the acid or base concentration in the body. You need to control pH by using buffers of hydrogen. So if our hydrogen concentrations get too low, if our hydrogen concentrations start to fall and we end up in a basic situation, then the body's going to add some more hydrogen ions in there to try and balance that. The flip side is if our hydrogen concentration starts to rise too much and we end up acidic, then we need to start absorbing those hydrogen ions. All right, so that's it for today. Hopefully that was helpful, and stay curious. Thanks a lot, guys.